Let's get some more practice. First, let's find the third degree Taylor polynomial of e to the x centered at 2. Just like before, we'll need the first three derivatives of e to the x. Again, this is easy. They're all e to the x. Then we can plug this into the general formula to find that the third degree Taylor polynomial of e to the x centered at 2 is e squared plus e squared times x minus 2 plus e squared over 2 times x minus 2 squared plus e squared over 6 times x minus 2 cubed. And now, let's use Taylor's inequality to give an upper bound for the error possible in using this approximation of e to the x on the interval 1 to 3. Since we're approximating using the third degree Taylor polynomial, we first need to bound the absolute value of the fourth derivative of f on the interval 1 to 3. Again, since f of x is equal to e to the x, the fourth derivative of f is, again, e to the x. Just like we found in the previous example, e to the x is increasing, and so it attains its maximum at the right endpoint of our interval. In particular, the absolute value of the fourth derivative of f is bounded above by e cubed on the interval 1 to 3. So, by Taylor's inequality with m is equal to e cubed, we have that the error r sub 3 of x is less than or equal to e cubed over 4 factorial times the absolute value of x minus 2 to the fourth. Again, on the interval 1 to 3, we get at most 1 unit away from 2. Therefore, the absolute value of x minus 2 is bounded by 1 on this interval. So, this quantity is bounded above by e cubed over 4 factorial times 1 to the fourth. And if we compute this number, we get that the error is bounded above by 0.837 on the interval 1 to 3.